So all right, so the final thing I'm going to do today is we're going to go briefly through how you would vary your cell size based on a field that you have defined. And this field can come from some function that you've created. It can come from a spatial database that Pilot uses, or any other thing that you can think of. But you have to be able to apply the field over a mesh that you've already created. So that is what we're doing with this Python script. So what we've first done, we went through and created a mesh within Qubit using constant cell size so that all of the cells are approximately the same size. And then what this Python script does, it reads the Qubit mesh, which is the Exodus file, the whatever.exo file. It's this file. And that's why we need this netcdf4, because a Qubit Exodus file is actually a netcdf file. So we need this Python package to be able to read the netcdf file. We also need NumPy. We need spatial data, which is provided as part of Pilot. And so we read in our mesh. We're also, in this case, we're going to read in a spatial database, which is a fake, say, material properties. And I believe this one has just a variation in the z direction. And then using those, we're going to say we want the cell size to be a function of these material properties. So we read the things in. We read in the spatial database. I'm not going to go all the way through this. We query the database, and then we create a cell size field that's a function of this shear wave velocity that we've read from the spatial database. And then this field is put into the Qubit mesh. In a similar way, we're going to put another field based on an analytical function here, and we're going to create another size field that is just an analytical function based on the coordinates. So once we do that, we put those fields into the uniform resolution mesh, and then within Qubit, we're going to read that mesh. We're going to recreate the geometry, and then we're going to create a new mesh using the fields from this mesh. So to do that, I've already set my new directory. We're going to open up. I'm going to do the analytical function one. So we can open that. So first we're going to just do the same geometry that we used when we did our analytical function. We also have to, let's see, in this case, we're not using SI units, it looks like. So it's a very simple geometry for this problem. It's just, this is, say, crust overlying a mantle, and we have the two volumes on either side of the fault. Then what we have to do, each of the blocks within our geometry has to be associated with one of the blocks from our uniform resolution mesh. So that's what we're doing here. And it also needs to be a tetrahedral mesh, the same one as we're using here. And I forgot to mention that that the cell size, Qubit cell size, the sizing function only works with either triangular or tetrahedral meshes. So we're going to loop over the volumes here. and associate each block. And then we're going to say that the sizing function for that block is type Exodus. So we'll go ahead and do that. So there's a loop that we're okay, so it's associating all those volumes with blocks. So then once we've done that, we're going to say that all of the surfaces have the sizing function type of Exodus, and all the curves have a scheme of stride, which I believe allows the points to move along the curve. So we've done that. And then really, all that's left to do for that is we mesh the different volumes. So we'll mesh the viscoelastic part, that's the lower part first. So what you'll notice if we look at, you'll see that this is now a variable resolution mesh rather than the uniform resolution that we had for our initial mesh. Now we'll do the same thing for the top two volumes. We're going to then delete all of the mesh. We're going to smooth all of this. We're going to delete the volume mesh, but we're going to smooth the surface mesh using this condition number criteria, rate of 1.2. Okay, so we've smoothed the surface mesh, and then we're going to mesh the whole volume. So in this case, we'll go ahead and look at the quality. Let's see what we've got. So you can see right now it goes from 1 to 2.42. And if you look here, it does essentially a histogram. So we don't have that many bad elements, but it's still, if we can, we want to reduce that condition number still more. So to do that, we're going to do a loop. We start off with a condition number of 2. We're going to do a loop of 4. We'll clean up the volume at each step, and then we're going to smooth it using the current value of the condition number and do the smoothing, and then we're going to reduce the condition number by 0.1 for each step in the loop. So we'll go ahead and do that. Okay. It may take just a little while for that, but in the meantime, if there are any questions about this, okay, so it's finished. We'll reapply this and see what we've done for improving the mesh quality. And now what you can see is that the entire mesh has a condition number no higher than 1.81. So that's a pretty good mesh there. So now that we've done that, In this case, since this isn't a real problem, we haven't bothered applying boundary conditions, but you can do that. But we're just going to export this mesh. Okay. So what I'm going to do now, I'm going to show you, now we're in ParaView, which can read Exodus files as well as other types. So we'll look at, well, first of all, look at what we started with, which is this uniform resolution mesh. So we'll look at, and we'll look at, so this was the sizing function that we defined over a uniform resolution mesh. Then, using this sizing function, we had our Python script, or well, the Python script applied this over the mesh. Then we went into Qubit, imported this mesh to associate with the blocks within Qubit. And then we end up creating a new mesh that's got variable resolution using that same sizing function. So does that procedure make sense to people?
One thing to add is that in these examples, both in the, not so much in the 2D example, but in the 3D example and in this qubit sizing example, is we used Python to generate the journal files, and then we used, in this cell size example, we used Python to augment the Exodus file. And so if you're not doing mechanical engineering parts, which is what Qubit was really designed for, if you're doing more geodynamics parts with non-planar surfaces coming from geologic models, coming from DEMs and so forth, usually you have to do some sort of manipulation of the input to get it into Qubit. And because Qubit does understand Python, so you can actually, you could bypass the journal files and do everything in Python if you prefer that, but really the Python is sort of not that much different than just generating the journal command. And so our procedure has generally been, let's use Python to generate the journal files, which then we can play in batch mode. They're very independent. We can use, within our own Python files, we don't have to use the Python that comes with Qubit. So we can take advantage of all of our geographic projection libraries and so forth to do any projections. We can use spatial databases, everything that, all the tools we have with Pilot to generate the journal files, and then we can run the journal files. And so as you go forward and sort of think about how you're going to get your geometry into Qubit, you know, you can use whatever scripting language you want. But remember that you know, something like Python, where you have access to all these other tools, whether it's linear algebra, curve fitting, and so forth, becomes a pretty powerful set of tools that you can use to generate your models.
Yeah, you can see the all these external packages are really handy. Like NumPy is probably the most commonly used, but like I said, to read this, there's netcdf4 package. There's an H5Pi package, which lets you look at HDF5 files, which is one of the pilot output types. There's also a SciPy package, which has a lot of packages that kind of build on top of NumPy, so you can do some really powerful things.
in the greens function example, that'll be session 3, we'll use h5py as well as a simple inversion in Python to interact with.
So
we've got about half an hour for questions. I see some evidence. So the question is, for a simple, it would be easier to use bias command instead of material properties to size.
Bias applies like there's a dual bias which applies over a surface, and bias applies along a curve. So it's actually easier to use the sizing function for this problem, because otherwise you have to add in extra geometry that you wouldn't need otherwise. You would have to put in some curves along which to apply a bias. To get one that's centered like this, it would be difficult, because the dual bias, if you just wanted to grade, here, I can show you. If you just wanted to grade, say that you didn't have this side, if you just wanted to go from here to here, you could have a curve where with a set here and then apply a bias along this direction. But since you have both sides here, I don't know, maybe then you would have the complication of how to apply the bias down within this volume here. You would have to define some more curves and surfaces. So actually, I find the sizing function very, very handy. I think if for a simple 2D problem, you wouldn't bother with it, I don't think. But for a lot of 3D problems, it makes your geometry much simpler if you can only put in the geometry that you actually need, rather than putting in geometry that you need to vary your mesh resolution. Spatial data is that Brad basically wrote spatial data, and that's how Pilot gets all of its spatially varying information. It can be boundary conditions, material properties, fault slip. All of those things are provided in a spatial database, and there's a Python interface to that. And that's what you're seeing in the Python script.
So it handles the non-dimensionalization objects as well. It has let's see, the spatial databases. It has the wrappers around the projection library.
Yeah.
So by using this with a spatial database with a coordinate system, it'll handle converting the coordinate systems. So you can use it separately as sort of you can use the Python functionality within a Python script to just do coordinate conversions. You can use it to do non-dimensionalization. It also provides an API for accessing this sort of wide variety of spatial databases. There's In addition to the simple ASCII files, there's also grid ASCII files. So if you have a lat-long grid of data points, you can use the spatial data interface to do efficiently querying of that models.
Yeah.
And spatial data isn't discussed separately from Pilot in the manual, but all of the various components are discussed within the manual.
Let's see more typing. Oh, you already did that.
Yep.
Oh. Okay.
Any other questions? As for trellis, we're not quite sure. The syntax for creating splines and net surfaces looks to be the same between Qubit and trellis. There may be some odd internal functionality that we're missing, or I didn't see anything in the journal files that looked sort of suspicious in terms of we create the splines directly from coordinates.
Yeah.
So it looked pretty straightforward in terms of what we were doing.
Yeah, between now and the next session, maybe one of us can try out the trellis and see what it does differently.
One issue would be to run, if people can run the 2D subduction example using trellis and see if they get the right information, because if they get the right mesh in that one, then there's something funky about the 3D example compared to the 2D example. Any final questions?
Spherical Earth model.
So Pilot recognizes Cartesian coordinates. It does not recognize spherical coordinates. The projection library does include support for an Earth-centered, Earth-fixed Cartesian coordinate system. So the two main options are really to, you can create your, basically in any case you have to transform into a Cartesian coordinate system. So whether you sort of set up your own Cartesian coordinate system or you use one of these geographic related Cartesian coordinate systems. Those are really your two options at this point with Pilot. And part of that's, essentially you can do all the geometry within Qubit in terms of, complex curved surfaces that match, a good chunk of the Earth if you want. And there is, using the Earth center fixed coordinate system, you can translate from latitude, longitude, height relative to either the geoid or the Earth surface to a Earth center Earth fixed coordinate system. Generally, we haven't applied Pilot to domains so large that you really had to take into account curvature of the Earth into account. We've been doing sort of the 1,000-kilometer length scale, which curvature of the Earth doesn't play much of a role.
Yeah, we did. The one difference to keep in mind is that there's a different way of handling gravity if you have a problem like that, which is also handled within spatial data. But I can't quite remember the details of how it works. Several thousand kilometers? Well, for several thousand, it could be. Yeah, and if that were the case, you probably would have to look into creating your own curved geometry.
Again, a lot comes back to what type of data are you trying to model, and what are your constraints, what's the uncertainty in those observations, so it really depends on this, whether you're doing a several hundred to 1,000 kilometers, probably doesn't make that much difference. But yeah, at several thousand kilometers, then it's going to start.
Yeah.
Make a difference.
Huh. Okay. So for Tohoku, well, yeah, that might make a difference. I mean, you can do some simple calculations to see how much it makes. Like, say, assume a spherical Earth, and then see how much deviation from that there is at a distance of 2,000 kilometers. And then Anthony says that the 2D subduction runs okay.
So
what?
I think this could be an apropos, possibly an issue or something like that, due to, perhaps, one option is if when you play the journal files, if that these the apropos commands do begin with a comment character. If you're playing the entire journal file, then it could be that there's some difference between Trellis and Qubit in exactly what apropos commands are supported. If you're selecting commands, because the apropos commands begin with a comment character, sometimes it's easy to skip over them and miss that units equals SI at the beginning. Those journal files for the 3D meshing didn't have any apropos commands in them. So that's a little odd.
Yeah.
But it does look like maybe Trellis could be a little buggy, because it doesn't look like Qubit 14 has any of these problems.
Yeah, I'll have to have a look at Trellis and see what it does differently. So,
Any other questions? So while we may be waiting, I did resurrect the partial recording from session 1. I had actually forgotten to stop it, so it has an extra hour at the end. We'll cut that down when we do our splicing. This one looks like we're still recording fine, so we'll get the link for this one up as soon as we're finished here. We've been accumulating questions in the Q&A log. I have everything formatted from this morning's. We're trying to organize them into sort of topics, so you won't see them in the order they were answered. They'll be sort of ordered by meshing, pilot features, pair view, qubit, sort of separated that way. But those will be uploaded, updated with this latest questions from this afternoon. As for between now and Wednesday, when we have our next session, we strongly encourage you to play around with Pilot and continue to, look over things, learn, get stuck, ask questions, and hopefully come ready for our next session. We can answer questions that you have in other topics, as well as we'll attack Green's functions and then solvers on Wednesday, coming back on Friday with fault friction and learning in parallel. So final call on questions for today.
yeah. One other thing, if people get ambitious, you could always take something like the the sizing function example and modify it to run some of the problems that are in 3D Hex 8. You would have to make a little change in the geometry because there's the vertical fault goes all the way down for 3D Hex 8, but not for that example.